Hello everyone, welcome back to 3 Deviations. In today's video, I would like to talk about the integrals of sine and cosine. Now to do this, we will be looking mostly at some theory-based examples, and these are going to involve some of the cases that we integrate with sine and cosine. And when I say we're integrating with sine and cosine, I'm talking about when we are going to be integrating something like sine to some power m of x times cosine to some power m, or some power n of x dx. And of course, we can mess around with these arguments, we can mess around with some of the constant terms, of course, but it's all going to boil down to something that looks a lot like this. And we're going to need to be looking at that. So we're going to be spending the next little bit of our Unit 6 talking about that. Let's get started. So let's start with dealing with some of the cases. Well, this is going to be the topic of today's video. In the next video, we'll be looking at some more examples. So here's the cases. There's case 1. So again, we're dealing with the integral of sine to the m of x, cosine to the n of x dx. So for the first case, we assume that the power of cosine is odd. So n is going to be equal to 2k plus 1. We can rewrite it. And we're going to be using this Pythagorean identity. Now, this Pythagorean identity is really just a rewriting of our sine squared of x plus cosine squared of x equals 1. This is kind of our unit circle definition that we have. And we're going to be fooling around with that a little bit in our videos on these trigonometric integrals. So once we have this, we can now make a substitution. So what we do is we take our integral, the original integral, sine to the m of x, cosine to the 2k plus 1 of x dx, and we assume 2k plus 1 because it's odd, and we work on splitting up this integral. So what we do is, if it's odd, we are going to take the cosine of an even power, and we're going to separate that from a single cosine. We're going to separate these two guys. And what we're going to be left with is the integral of sine to the m of x, cosine squared of x, quantity to the kth power, times a single lone cosine of x dx. Now what this allows us to do is this allows us to apply that Pythagorean theorem that I was talking about. So what we get is we get the integral of the sine of m, sine to the m of x, and then we apply, because we know cosine of x squared, or cosine squared of x is equal to 1 minus sine squared of x. So then we get 1 minus sine squared of x to the kth power, and that's times cosine of x. Now, as you can see, we are really nice and prepared to perform a u substitution, setting u equal to sine to the m of x, because we've got the derivative right here. So we are prepared to make that substitution. And then we just have some simple arithmetic and algebra. Then we need to deal with some of the u's there. Okay, so now let's talk about the second case. This is the case where the power of sine is odd. So when the power of sine is odd, then that means that m is equal to 2k plus 1. So now we're going to rewrite the Pythagorean identity. We're going to use it in this form. We're going to use it in the form sine squared of x is equal to 1 minus cosine squared of x. Now we're going to do something extremely similar, and we're going to be applying this identity. So this is going to give us the integral of sine to the 2k plus 1 of x is equal to cosine to the n of x dx. And we set this equal to the integral of sine squared of x to the kth power times cosine to the n of x times sine of x. And as you can see, again, we are prepared to apply this Pythagorean identity there, and we're going to be left with the derivative there. So we set u equal to cosine of x once we are ready. So this gives us the integral of 1 minus cosine squared of x, quantity to the kth power, cosine to the n of x, sine of x dx. Again, prepared for that u substitution as we have the sine of x there. Again, simple arithmetic and algebra that will take us to our antiderivative. Okay, so finally we have one more case to deal with. And this case says that if we're dealing with the integral of sine to the m of x times cosine to the n of x dx, and both of the powers are even, such that 2k equals 2k, then we are going to need to look at some other options, some identities that we want to apply. Okay, so the first identity that we want to apply that we've actually been using to solve some of our integrals with reduction is sine squared of x is equal to 1/2 of 1 minus cosine of 2x. And of course, we have a similar identity for the cosine function. This gives us cosine squared of x is equal to 1/2 times 1 plus cosine of 2x. And finally, we can also use the identity that says sine of x times cosine of x is equal to 1/2 sine of 2x. Alright, well that was our video on our trigonometric integrals when we're dealing with sine and cosine. This was just the theory with these cases, and we will be looking at some more concrete examples in the next video. So we're kind of going to be dealing with this in groups. So we've got a sine-cosine group, so sine and cosine. Then, so we're going to do a video, we've already done the video on theory, then we're going to do a video on examples. And we're going to look at tangent, and tangent is kind of by calculus coupled to secant. So we'll be looking at tangent and secant. We'll do a video for cases and a video for examples. And then we'll look also at cotangent and cosecant. And we'll